has thank you.
There we go.
Has many initials behind her name, including PG, PMP, CVID, and is a leader in the energy sciences and sustainability sectors. She merges extensive geoscience expertise with a steadfast commitment to sustainable energy. As a project manager for Proaho,
Yeah.
thank you, corporation, and I clearly didn't practice, it was nervous. And owner of Orca Switch Solutions LLC, she leads the charge in driving innovation in environmentally sustainable energy solutions, establishing herself as an essential energy translator in the industry. Her diverse career in the energy sector includes roles ranging from field and applications engineer to geoscience manager at Baker Hughes, geoscientist at Eneos Geosolutions, and petrophysicist, I can barely even say her qualifications now, at Apache Corporation, QEP, and SM Energy. Katerina's significant impact extends to consulting on new energy ventures, where she has been pivotal in guiding the industry toward a more sustainable future. Her robust academic background includes a Master of Science degree in Sustainable Management from the University of Wisconsin at Green Bay, and geology from RWTH. I'm not even gonna try. University in Germany. Sorry, little hairball with pronunciation. Finally, I'm gonna truncate the personal just a little bit so we can get rocking. Katerina is the co-chair of the Women's Network of the American Association of Petroleum Geologists. And outside of her professional endeavors, she serves as co-CEO of Her Family in Colorado, which I'm sure many of you do the same. Although, unlike me, she's raising 3 boys and a husband. Wait for about 10 minutes. It is her belief that the power of early education in belief systems and social awareness is crucial, aiming to foster a more inclusive and successful community. This perspective underpins Katerina's blend of career success and personal dedication to environmental sustainability and social responsibility, showcasing her as a leader with a visionary approach to promoting sustainable and inclusive energy solutions. So please welcome Katerina.
Well, welcome everybody. Thank you for being here. And I hope this journey is a learning journey for all of us. It's basically the encapsulation of the knowledge that I gathered over my career, starting pretty much at from the time of my PhD, where I started with being influenced by geothermal. So if you want me to, okay. Perfect. So the goal for me today here is to generate a bridging gap, or bridging the gap, I should say, to building to the key building blocks that connects us, oil and gas, with geothermal energy. In general, both of them have to do with the drilling piece of it, right? But also with the reservoir piece of it. So with that, I'll go to this either. Oh, sorry. So geothermal is not new. Geothermal in terms of generation for power was exploited already in 1904 in Larderello, Italy. I grew up in Italy, so I was very close to this. So geothermal was, like I said, part of my story from the beginning without me even knowing that it was there, right? But power generation has been discovered for geothermal reservoirs early on, and in that case, it's more a measurement of steam and having steam turbines. Now, as I will show you, we'll go into the discovery of a lot more applications of how to extract the heat from the subsurface and turn it into power. But in general terms, this is a 2020 snapshot in time in terms of power generation. And the US is leading, has been leading for quite a while too, in terms of, this is gigawatts, right? The 1 gigawatt club here. So that's US, Indonesia, Philippines, Turkey, and New Zealand. And they've been at it for, like I said, for quite some time. But the efficiency piece, I think that's a piece that just recently is coming to get accelerated here with the influence of oil and gas. And just to give an indication here to that, this is this is the screenshot or the snapshot for 2024. So that's last year. And we still have the top 4 there being the same ones. But also on the bottom, we have other countries coming up in terms of developing their geothermal potential, right? So it is already within 4 years, you see countries on the map that were not there before. Iceland and Japan, they were there, but others, as well in terms of power generation. Germany is one, for example, that is expediting the learning curve and trying to catch up with these guys. But it is always a matter of the global energy mix. And geothermal still gets a little bit, within the level of the noise of renewable energies, right? So that's something that the global market, as well as other countries in general, like the International Renewable Energy Agency, they're saying, that there needs to be a lot more collaboration from other energy providers and companies that help this transition to be more meaningful, right? The potential is there, but how we're going to make it happen. And then this is actually from a report from ExxonMobil. There's, the potential that we need, and we see it coming, is through the increase in population and the requirement for them, or the need for them to become on the, energy poverty being something of the past. Everybody wants to be on the energy safe side, right? So that's the goal. And the population increasing, we need to provide a wide spectrum of potential energy sources. So we got the challenge, right? But we also got the key to the solutions. And this is something, like I said, is something that I discovered and enjoyed discovering throughout the last few years of my career, but like I said, from early on as well. So what we'll be doing today, we'll be looking at some subsurface key aspects. Me being a subsurface person, I like to talk about it for sure, but I'll try and tie into the aspect of what the challenges are, and how we can get to a solutions that can provide more applications for geothermal energy throughout the system of our energy-hungry global society. So geothermal reservoirs. The main piece to geothermal is obviously finding the heat, right? The average geothermal gradient, that is the heat at which the increases with depth, is about 30 degrees C, and it can go up to 60 or so. The 61 is Labdarello, Italy, right, where you don't have to go too deep to get to that 60 degrees C per kilometer. And then we're dealing with Fourier's law of conduction, and then natural geothermal reservoirs, they thrive on the reservoir convection. So it's like a hot pot, right, under the surface that we're tapping into. And obviously those are not everywhere, but we have come up with understandings of how we can figure out ways to be able to tap into the geothermal gradient of wherever locations you might have, right? And make the most out of it. So we're dealing with the heat source, right? We're having to find that. We need to find permeable porous reservoir rocks. Sometimes, and not always, but sometimes it's just igneous rock. It's like your granite countertop, right? How you're gonna get any pore into that thing, right? So that's how some innovations happen here in the last few years. I'll be touching upon those too. For conventional geothermal systems, you need some kind of water movement or fluid movement within the reservoir to be carrying the heat from your wellbore back to the reservoir and heating that constant flow, or having that constant flow of hot fluids. in an area like, again, like the geysers of North California, close to Yellowstone Park, right there, you have a natural occurrence of heat coming from, not too far into the subsurface that you can recharge your systems. An impermeable rock is there to keep the heat, and the pressure such that you can keep on having those convection cells of heat transfer. So these are the requirements or the elements of conventional geothermal, and that's what we've been known for so long, right? The picture on the top right is actually from Iceland, volcanic desert basically, and then they put those geothermal plants on top to harvest the heat. But this is a geothermal power generation chart for to get an idea of what all can be done at certain types of heat. Yes, go ahead. So you can start having fish farms, with low temperatures. We can have greenhouse, a constant heat supply. When the temperature changes all around the greenhouse can be kept at a constant temperature with geothermal energy. This is what happened in the Netherlands, for example. They obviously are famous for farming a lot of tulips and things like that, right? So they use their little geothermal heat that they have, which is not the hottest, right? It's not steam or anything, but that has been used in the last, I would say, decade or so to keep the tulips blooming all year round. So there are multiple occasions, not only from an energy source, but also from an agricultural and food, food supply. Another piece that, with growing population is a big quest, right? In having enough food for everybody. But so you can see here the hydrogen production, right? We're talking here higher degree heat, and with all these scalable pieces, you can attract or put different power plant types on top of it. So we have the binary cycle, we have the flash steam, and the dry steam. So the flash steam, for example, that was Larderello, that was in Italy there, and that's also parts of California. That's what's happening there too. But binary cycle is basically one where, excuse me, they found a way to have a fluid in the system all on the surface that can boil at lower temperatures than water, for example, and use that to spin turbines, right? And then create power. Versus the flash steam and the dry steam, which are, you just basically put a pipe in the ground and collect the steam and then make that turn the turbines. With recent, maybe 10 years ago or so, a bit less, they also started to put supercritical CO2 into the systems to have that as another way of capturing carbon and also producing power. And then there is the thermal electric piece, but the line on the conventional power plant types, those have been around for quite some time. But they're getting optimized, especially the binary cycle one is getting optimized now to once they spin the turbine, the turbine, also has some kind of energy deficiencies. Those deficiencies have been worked at and looked at to increase the power generation as soon as that, turbine spins, basically. So there's a lot of momentum, not only on the reservoir evaluation and extraction of the heat, but also on the on the surface side of things in terms of facilities and things like that. How to capture the heat best, right? Without losing too much to the environment and the surroundings all around it. But so yeah, that's an important piece actually in terms of geothermal power generation. Okay, yeah. And then there is, more subcategories in terms of the reservoir, the geothermal reservoir itself, and it's divided up by their by certain types of temperature ranges. And you can see here, according to various studies, that's how they came up with these definitions. But the diagram on the right is from Siemens. Siemens is one of the big producers of those pumps and things like that take the heat and convert it into power. So they've been at it as well for a while. But you can see the complexity there in terms of pumping cold water down into a hot fractured reservoir and then having producing elements or producing wells that combined will bring the power to the facilities that will collect it and bring it to the grid. Some recent advancements in geothermal were the enhanced geothermal systems as well as the advanced geothermal systems. So one has a similar concept there where you put cold water down into a fractured reservoir, or now with the recent approaches of fracking, actually, right? Using unconventional oil and gas knowledge and fracking a reservoir that can both be igneous or some kind of a shale as well. They're looking at that as well to create pathways of heat for the fluid that they pump down and be captured with producing well. And then that one creating the power, and whatever comes back, and if there is anything left, right, and add it on, it's a cycle as well, right? With the AGS, this is all closed loop. There's no water interacting with the subsurface, but the power cycle of the heat is still happening, right? And what a lot of countries and things like that, obviously, they like the piece of AGS, but in terms of power production, they're about the same. They all have, just like oil and gas, they have an IP, right? EGS in particular. But that's something that you need to take into consideration, and how far you can extend it or have it recreated. That's all learning curves that are happening right now. But those are the most recent adaptation of geothermal power generation. So the conditions that need to be in place for geothermal prospect are quite a few pieces, but it's a combination of all of those that will help you determine the amount of power that you can create or out of your geothermal reservoir. So obviously high temperature, high porosities, as we mentioned, and the permeability piece is something that, like I mentioned as well, with the igneous rocks and so on, you either have to have a natural fracture system in place that you can stimulate or create your own, right? And fractures, they're there to transfer the heat and keep the heat transfer open. Mineralogy is key in many ways, just because the rock types that you're dealing with in the subsurface can conduct heat in a different way or with different properties, and accounting for it is very important. Water chemistry, the one that you pump and the one that is already in place in some cases is critical. Actually, geochemists are the most favorite physicists from the geothermal part of things. Geochemistry is quite critical because the water, as you saw, there is water or some kind of fluid involved with the heat transfer, right? And if that is of a certain degree of composition that can clog or pipe, the pipes up, that's critical. Actually, California is the one that is, for example, as you saw, US has been producing quite a bit of power, and in California in particular, Northern California, and they've been dealing with either water shortages, the water quality in terms of chemistry, and then it's clogging up their systems, right? The water chemistry is quite important. At this point, I know that they're using a lot of wastewater from the surrounding areas to feed into those Northern California plants for geothermal power production. But the power production has decreased because of a lot of these issues with the water chemistry. One piece that, the formation in the reservoir structure, obviously, again, now instead of, the you want to see where the formation is, but when it comes to your igneous rocks, it's more like a big, big body that you want to understand. But what you want to understand more is where the isotherms are. So where the levels of temperature are and how they change over depth. And so you map those out as well. You use a lot of geophysical tools for that, gravitic magnetics, and log data where possible. The geomechanics, the way the rock breaks is going to be important, and I'm going to dive into it a little bit later as well. Yeah, so this is a 2011 map, of the of SMU's geothermal laboratory. They've been at it for a while as well, in trying to understand where the heat map in terms of flow, so the capacity for a rock to transfer heat. This is pretty much what it is, right? Over the US. And I know that there have been a lot more maps like this being created just of recent. This is, that's just for us to understand the advantages. And you can see here, in areas where we have certain sedimentary basins that we exploit for oil and gas, like the southern, from West Texas there, from the Mexican border all the way up into Louisiana and Arkansas, you can see that there is a heat transfer happening. This is due to some geologic events that happened that allowed the mantle to get closer to the crust and therefore heat up some of those sedimentary basins. So this is not igneous rock. This is the Eagle Ford, the Austin Chalk. And I was fortunate enough to write on my master thesis last year about looking at exactly that one, that little sliver there of hot rock that can be used for both oil and gas as well as geothermal energy production. So, well, now I'm going to take you into my world a little bit. Don't be scared, it's all good and fun. So, logs are my friends. So what do we want from log data? Usually, right, we want to understand the lithology types. And again, and in geothermal, it's another important piece. Porosity, that's also another important piece, both in oil and gas. And that's why I put my two little icons both up there. We have the fluids in the system, the gases, the oils, the brines, the other fluids that we want to understand, and how they react with the fluids getting pumped into. Again, there are so many ties into unconventional oil and gas that is really scary. Permeability, bless you, yeah. Permeability, the easiness of the flow, and that's one of the pieces that we can have control over, as well as geomechanics. Understanding geomechanics, both in geothermal and unconventional oil and gas, is quite critical. As the HFDC sites and all of those experiments that we did on a big scale for unconventional, this is something that we need to do on geothermal as well, to really understand it to its fullest. So, parent-child interactions, that's something that we'll also have to do with, or be better understood with geothermal. So we're starting, so everybody is welcome to chime in, right? So just another overview of other instruments or measurements that can aid the understanding of the subsurface. And this is just, this is your usual logging suite. But again, it can all be used for geothermal as well and be quite informative. So one of the main tools that we use for geothermal understanding is the acoustic tool, which is basically sound waves going into the formation for you to be able to understand the way a wave travels through the rock. It tells you a lot about how the strength of the rock, right? And with that, you can determine how the rock will break if you will stimulate it with fracturing fluid, which in EGS we do. Imaging tools, those are, very fancy looking tools, but they give you a literal image of your borehole wall and the top. Let's see if I can get no. I saw it for a second. Okay. Well, right here. No. I want to point, but that's, you see a well bore basically, and you see the arms of the tools stretching out, and that's how the measurements on these little pads, those little dots there on the bottom in the middle, those are resistivity measurements that get taken. And now we're going into resistivity and acoustic measurements. So we're expanding our knowledge on tools that can help us further into the geothermal data or subsurface evaluation. So these are all great tools that can be used. And the reason why is that you can see natural fractures. You can see breakouts. The breakouts can tell you how the wellbore stability is in situ, so down hole. So these are your eyes basically down in the hole, which for geothermal and any other reservoirs are very useful information points. So the petrophysics models, have building blocks that again can be used in many ways, and as well, and in particular for geothermal. There is the standard logging suite of density neutron resistivity logs. You can add advanced techniques for geothermal systems there, which is the temperature log usually is something that always has to be run, right? And it's probably sometimes the minimum tool that gets run. The acoustic logs, like I said, are logs that can tell you a lot about the rock physics, so the composition of your actual rock, the composition in terms of mechanical integrity, right? The image logs give you an image literally of your borehole wall and therefore an identification of your fracture system if you have it. And then formation evaluation, so getting all these products into a model then provides more information of the collaborative of your fluids in the system and the matrix in which they're in. So this is, I'm not going to go through it one by one, but this is the unconventional reservoir workflow, and it starts all very much the same. One of the few differences there is that you're taking into account the total organic carbon, so the TOC, and comparing that to geothermal reservoir. Again, you got to do the same thing in terms of taking care of your log information, calibrating it, and normalizing it. And if you have core data, you will want to tie it back to that. So rocks are always there to tie things back. But the bottom piece, the number 6 there, is what it all ties down or brings it back to geothermal, which is tying your mineral models to thermal property. And that's what helps you then being able to extrapolate those properties and being able to put them in a 3D model. And then that's how you can determine where your hotspots literally are. So yeah, and critical understanding of geomechanics, like I mentioned before, how does the rock break? This is something that approaches the EGS piece of geothermal. Oh, and these are the isotherm lines that I was talking about before. So this is what you want to identify as well. When you have your igneous rock intrusion through the crust, basically, you want to understand how the heat flows through that, and logging tools can help you with that in identifying that, along with the geophysical measurements. Rock mechanics, I'm not going to dwell too much into it. That's, again, a critical understanding for both unconventional reservoirs as well as geothermal reservoirs for those particular modules, which are the Young's and the Poisson's ratio, as well as a bulk modulus. Core data integration, a critical piece. This is something that I discovered last year quite intensively too. The amount of rock data collected in geothermal reservoir is quite minimal. And so trying to defer or make some kind of correlation like this might not be always happening, but this is a collection of multiple points here on the right-hand side. So you have multiple reservoirs and you're trying to find relationships there between that. But it's critical to understand porosity there and core mineral information. So these tie back into a model that you can then distribute into your softwares and to 3D space to see it all clear. But these are, like you see on the y-axis, that's the thermal conductivity piece and how they relate to porosity, right? So there is a tie there that needs to be understood for every of your reservoirs. And when it comes to distribution of properties, many times we go back to rock typing, which can be done with cluster analysis and things like that. You need to align your mineral to thermal properties connections. And once you have that, machine learning can help you create facies or rock typing that can be distributed and adapted to any new log that you might get or any log that you have. Usually we start with the most amount of data that you can have or can get, and then try and dumb it down, so to speak, and use rock typing or facies distributions to be able to still propagate properties throughout your models. So I wanted to show a few case studies here of where log data was collected for geothermal reservoirs. And this is one of my favorite tools, the NMR tool, which is nuclear magnetic resonance tool. It's basically an MRI scanner that we're putting down hole. This one was used for one of the geothermal reservoirs that they were looking at in the Netherlands. And this is from Bradley et al. But this is the NMR tool is a permeability indicator, which is one of the few tools out there that can do that. Basically, while it collects the data, it can give you that index. Those indexes are all based on Gulf of Mexico sands, the best case scenarios, but it's still an indicator and good enough for you to be able to determine if there is fluid movement within your system. And this is in, actually, it's a carbonate-rich formation here that we're dealing with. The gamma ray is very clean. But there is production logs too that indicated that in this case, there was a temperature gradient change because of the spinners spinning at velocity change in the spinners. We also had a temperature gradient change, but no change in the velocity of the spinners. So looking at the acoustic tool, which also not only giving you the rock, the geomechanical aspects of it, nowadays we can look deeper into formation by basically listening to the further arrival. So you're looking out into the wells, and here it's about 25 meters out, depending on the rock type, right? Do you have a bell or do you have a little bit of a clay piece that you're hitting on, right? So that is what gives it away in terms of how far out you can listen into. But with these methodologies that we have now, we can basically do something like a seismic aspect, or seismic interrogation of your sonic data. And with that, you can determine if you see some unconformities in your returns, and that can be related to faults or fractures in the system. In this particular case, it was a fault that was going out, and it was cutting through the wellbore right where we had that spinner change in the production log and the temperature decrease as well. So this can be either a thief zone, right? Or it can be a conduit for your fluids. This is another example from a reservoir very close to Lardelello, Italy. So you have images. Again, this is a 360-degree wellbore display of your rock all around the reservoir. And you see how the increase of fractures, which are given out by those little tiny triangle with the tail on it, the tadpoles, they're increasing at certain points within your reservoir. So understanding that piece and then tying it back to your sonic data makes the full picture of your reservoir. And there is a cataclysmic zone, so basically all ruptured zone that can, again, be either a thief zone or not, right? So the understanding that piece helps you determine, if you need to close this part off to be able to keep the flow and the heat going or not. So catalyzing geothermal development, switching now away from the subsurface technical sides, there's obviously majority of the hurdles so far for geothermal have been on the financial piece. And the regulatory changes that just happened recently, I should say, in places like Texas, and also places like Utah and Nevada easing out. But Nevada and Utah have very well-known geothermal reservoirs, right? So they've been at it for a little bit longer. Texas just recently it wasn't quite clear who was the owner of the heat. It was clear of who the mineral owner is in Texas, but not the heat, and that now has been cleared. So that's now everybody's, going after Texas as well. But so there is an opportunity here to, and the Geode program or workshop, it's a program by the DOE that helps the collaboration between oil and gas and geothermal companies. And I'm fortunate enough to be part of it as well. And it's quite exciting. They're really trying to put a roadmap out there that should accelerate this whole process of, whatever we went through unconventionals, right? It was a learning curve. They're trying to expedite that and cram it into 5 years. So we'll see how that goes. But it's definitely there, and it's getting funded, and it's supported heavily by the government still. But again, the advancement of drilling and understanding that geothermal, as we found it maybe even 5 years ago, was dealing with they didn't know what PDC bits were. They still had the tricone bits, things like that. They were dealing with equipment that was also from the 70s and 80s in terms of drilling rigs and other equipment. This all can be expedited and being brought to the 20th century, literally, and therefore also, de-risked and being brought into a upscale mode that can be accelerated to use conventional, unconventional oil and gas knowledge. So the future perspective that I see here, the recent advancements and their potential impact, the way that also companies like Devon invested quite heavily in companies like Fervo, shows that they see potential of their knowledge of completions, drilling, and anything like that being one-to-one translatable to geothermal reservoirs is quite encouraging. And I think it should happen more, and hopefully will happen more often here soon. The role of policy and investment, if you don't know who owns the heat, who are you going to give the ticket to? So these things need to be taken out of the equation, and by having policies in place to do so. Private sector is also very much interested currently in being part of or having a piece of the pie, right? Basically, and it's good to see. But I think the momentum is there, and it's definitely happening as we speak. So the geothermal energy is definitely. It shouldn't be a sliver under the renewable piece of energy, sources. It should become a bigger one, and it's just a matter of putting the focus of what we already know and putting it right to work as we can right now. So so we truly hold the key. That's pretty much my conclusion, and it's all up to you guys to make it happen. No pressure there, but we have the knowledge. We know exactly how to risk assess everything and subsurface evaluate everything. So it's just a matter of applying our knowledge and taking it to the bank, literally. All right, with that, that's all I had. So I have some resources here of where I got the information and the nice pretty pictures. So any questions?
So how do you manage conditions over time? Like say 5 to 10 years, how much does it fluctuate and change? Is it a lot, or?
In terms of the reservoir heat?
Yeah.
This is part of a reservoir engineering conundrum a little bit. So because the amount of flow that you put through a pipe determines how much heat you're extracting and how fast, right? So that piece needs to be figured out. What balance do you want? And how much energy you want to produce. If the energy is your heat, you might need to put more wells in the ground, right? Just to extract more heat. There are, like the Northern California ones, those have plateaus as well. So you can see that coming. and you can model it. Yeah. So there are CMG is catching up on things these days, so we can use it for that as well. But there are already some old-fashioned softwares out there that do exactly that, the heat transfer and depletion of the reservoir, and how fast you can drain, to recalibrate. Yeah. Yeah.
So who owns the heat rights?
It depends on states. Yes, every state is different. And that's the other piece, right? So it would be good if everybody has the same rights everywhere. It's surface owners are in Texas, for example. They own the heat as well. So
We have an online question. Randy wanted to know, how hot does the temperature need to be to damage equipment? We drill oil and gas wells to hot temps.
yes, yeah, that's a good question, Randy. So there are limitations on the tools that we can run, right? For example, Fervo, they did log quite a bit, but the tools suffered. And what came out of the hole looked like an explosion in a microwave. No, it wasn't that bad. No, but yes, the limitations of how much heat a tool can take when it comes to logging are set. And what they do sometimes is either have a cooling mud go before the logging runs. LWD is another option, and that has been used especially for image logs. The other ones are there are insulators, just like your thermos cans and thermos cups. They put them around the tools, and they can log a little bit longer, maybe an hour or two. But there are these isolation options, so that people get innovative, as in many ways when you need to, right? But yes, it is a limitation. But for example, for the NMR tool that I showed, that was a sedimentary geothermal reservoir, so the heat was not as high, and therefore the tool was able to collect all the data it needed. Yeah. Yes.
So I hadn't heard much about the supercritical CO2 method. Do you have like a 3-sentence description of how that works?
Yeah, so they do collect it and they compress it such that it turns into supercritical CO2. For that you need to have another whole surface equipment, and it's an expensive piece for sure.
I can help you with that.
Yeah. Well, Kat is your lady, so no, but it is something that they've been using already, as there were test cases already in 2016 and so on that have been successful in doing that and using that as a fluid.
Is the CO2 getting sequestered, or is it part of a
It's a loop,
loop?
right? So it doesn't come out of the loop. It's part of AGSs, so closed loop systems like to use supercritical CO2 as it travels within that loop. Over and over again, and stays there. Yeah.
So like Freon in your house.
Correct. Yeah,
Cool.
That's
And it was
free.
part of that because it's naturally occurring there already, so you wouldn't have to bring in the water.
Yeah, or you can. Yeah. Especially, like California, we all know they're dealing with water shortages. That's why they were looking at this in 2016. That's a COSO. There's a COSO plant in California. You can look at them, and that's what they tested. Yeah.
A little extra CO2, so.
Yeah, we've got plenty.
What kind of water quality do you need? Can you use salty water, produced water, or?
Yeah, that's a good question. So there's, for example, the EGS systems that Fervo has, they are using a mixture of water, but the water that you can use, you want to have it that is being able to transfer and not being a pain, right? If it's salty water, the salt can dissipate. It can, go somewhere and find places to give you a headache, right? So the composition of that water is critical. Fervo, as well as Utah Forge, actually. Utah Forge, which is also in Utah, close to Fervo's Cape reservoir. They have done a lot of analysis on that too, looking at EGS, so fracking to create geothermal energy, way before Fervo did. So they have the test facility, and it's also governmental funded project.
Looks like you have another online question. What would you characterize the potential for US thermal development compared to New Zealand or Italy?
obviously bigger land mass.
Yeah, well, we have a bigger land mass. New Zealand has the plus or the brownie points that they're right on top of very active volcanic lands. Italy, same thing. Actually, I heard there was well, not in Italy, but in Greece, there is a volcano, earthquakes at the Santorini Island, which is an old volcano, just like the Yellowstone one. So we'll see what that happens, there. But having geology help you out is a good thing, especially when it comes to the amount that you need to drill down to get to the heat level that you need to get power generation quality heat. So I guess in terms of development, it's all a matter of getting the lineup of your surface equipment in an area where you don't have to drill too deep to get enough energy. In terms of energy, also, I haven't mentioned it much, but we're talking from kilowatts to 100 megawatts. Yeah. Yes.
What is the heat level that's being used now? So they're drilling to what heat level?
So the heat level is from 500 C to 100 C. So there's the whole span. And that's again it's not all for power generation, it's what you need it for, right? The sometimes, like the feasibility study that I did was looking at power generation for oil and gas equipment on location and it was enough in the Eagleford, it was enough to power your collection sites, right? Where you keep your hydrocarbons before they go out into the midstream pipelines. Yeah.
What's the difference in the water from the EGS system to the AGS system?
So the EGS system is something that should help you create fractures. It's similar. It's not. I mean, it is similar to what we use to frack in unconventional reservoirs for EGS. The AGS one is something that you want to keep in the loop, and you want to have it transfer heat as best as possible. That's why they're using also supercritical CO2, as it is a better conduit of heat. Yeah.
So with the AGS system, that like diagram that you showed, the underground sort of, is that cased?
Yes. Yeah, and sometimes it's it's not like a loop. I mean, it is. Ever, I forgot how you pronounce the Canadian company. They are doing that exactly right now. It's a very, I mean, it's a challenge really, because they're coming in from one end and they're trying to drill another well that ties right and connects to the other one. Yeah, so it is a major challenge, but they managed, and they had their test facility or tests in New Mexico, actually, on that particular Ever loop, and they're evolving as we speak too. So, but then the other, there's another one where they have two coaxial casings, one with a regular casing, I call it, and then there's a vacuum, it's a vacuum casing that is, again, vacuum is there to be able to transfer heat again better and isolate the heat to go in, right? So you go from the outside and drag the heat water into your vacuum sealed casing. So it's dual casing. Mm-hmm. Yes.
Do you see any investment or utility companies? Are they investing in this technology, or is it all government funded?
So the bigger investors are the Metas, the Microsofts, the Facebook, I already mentioned, then Google. Google is one of the bigger ones. Those are companies that have their headquarters in California and get good extra brownies on top from California State. But there are quite a few interested parties that are outside investors, and they are looking now to, again, for data centers, looking into developing geothermal understanding better for them to get that energy hunger that they have, right, in terms of data centers. Data centers data center companies in general are looking at geothermal very heavily right now. As it is something that doesn't require you to be in you can be in a rural area, right? So that's where they're looking to see where potential is. Yeah. Yes.
Talk about, is anybody repurposing like old verticals, oil and gas and verticals for geothermal?
Yes, so the Geode project is also looking heavily into that. The difference there, or the challenge there, at least that's what I discovered during my master thesis last year, was the sizing, the casing pieces of our production wells in unconventionals are too small for geothermal power production. It's all about surface. You need a lot more surface to contact the rock to get the heat to transfer it out. In oil and gas, you just want to be, as minimal as possible, but have enough to have your hydrocarbons flow. So it's not much of a surface of the casing. It's more of a surface contact in terms of fractures that go out into the reservoir, right? So yes, so that's a challenge, right? The repurposing of oil and gas wells can be happening, but it's at this point, it's not at a point where we can actually do it one-to-one. We would have to go in there and probably recase, take out casing and drill bigger holes. Yeah. Yeah.
I have a question.
Yes.
With that, what's the lifespan of a system without major repairs? Is it, do we have enough data to just kind of look at what
Yeah.
we can get from a site versus,
Mm-hmm.
yeah.
Yeah, so for conventional geothermal, like the one in Northern California, it's been going on for I think the 60s. They had to go in and do some cleanup of the pipes. The water again was basically shrinking their inside casings. And so that's the main rework that was happening there. So they can last. It's all a matter of balance between how much you pump down and then flow back, right? Yeah. So yeah. Yes.
Are you talking, when you say Northern California, is that the Calpine?
Calpine is one of them. They are collaborating, I think, also with COSO, but COSO one is the bigger one. Yeah.
It's Calpine Racetrack.
Uh-huh. Yeah. Yeah. Well, I hope I made you all enthusiasts now. Let's go out of the country. Well, thank you so much.
Thank you.
Thank you all. We would love everybody together for a group photo, please, before you all take off.
And then I just want to say a special thank you because Katerina is sharing her birthday.
Aww. 23 again. Yes. Thank you so much.
Over there. If everybody wants to stand over there for a quick picture around Katerina.